Good morning, ladies and gentlemen, and welcome to the SAIEE Rotating Machine Section webinar on design of a wound rotor synchronous generator. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on your device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel, and by default, the control panel is located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other, however, are encouraged to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, SAIEE TV. Find the registration link in the chat box and register. It's free to register. The recording of this webinar will be listed under the Rotating Machine Section playlist. A certificate of attendance will be issued a few days after this webinar. Before I introduce you to our speaker this morning, I just want to give you the narrative behind this webinar. That Tariq Rouhani is the SAIEE Rotating Machine Section prize winner from the Southbeck Conference held in Stellenbosch in January 2024. His winning paper discusses how generators for wind power conversion require a low torque ripple, as a high torque ripple translates to vibrations in the machine, affecting its structural stability and causing excessive wear on the drivetrain components. So Tariq Rouhani is currently pursuing a master's degree in electronic engineering. He is working on a project related to organ-on-a-chip technology as part of the biosensor node. Tariq completed his undergraduate degree in electrical and electronic engineering at Stellenbosch University with a specialization in energy systems. He is incredibly passionate about his field and has developed excellent problem-solving skills, which he applies with unwavering determination. I hand you now over to Tariq.
Good morning and welcome to all. My name is Tariq Rouhani. My presentation today is on the design of a 3 megawatt wound rotor synchronous generator and permanent magnet synchronous generator for wind turbines with reduced torque ripple. The presentation will cover the following: an overview on the paper, an introduction to the problem that was studied, a general overview of generators, the principle of torque ripple reduction and its importance in wind turbines, the optimization process used, as well as the design of the models and how finite element analysis was used on them. This leads to the last part of the presentation, which will be the comparison between the optimized wound rotor synchronous generator, WRSG, and the permanent magnet synchronous generator, PMSG, to determine if the WRSG is a good alternative to the PMSG. Generators for wind power conversion require a low torque ripple, as a high torque ripple will result in wear over time and create structural issues in the wind turbine. The study involved the design and the optimization of a 3 megawatt medium speed wound rotor synchronous generator and a permanent magnet synchronous generator. These were then compared to determine if the WRSG is a good alternative. The optimization process focused on determining optimal stator slot dimensions for both generators and rotor slot dimensions for the WRSG. The optimization process resulted in a reduction in torque ripple, but at the cost of a loss in torque output for both the WRSG and PMSG. The WRSG had the best torque ripple reduction to output torque loss. Typically, 2.75 to 3.5 megawatt generators are used for wind power conversion, as the high capacity means fewer turbines are required for generation, easier transportation and building. So for this study, a 3 megawatt design was selected. A medium speed of 375 RPM was also chosen for the study. As it offers a maximum efficiency and it has benefits as both low speed and high speed generation. Low-speed generators are not effective at converting high wind speed, while high-speed generators have increased centrifugal forces, so a medium-speed generator would be the best option. Additionally, the medium-speed configuration uses a lower gearbox ratio. Both machines also featured a 16-18 pole slot configuration. Machines used as wind turbines should have a low torque ripple, so a targeted torque ripple of below 6% was selected. A low torque ripple is desired as a high torque ripple translates to vibrations in the machine, affecting its structural stability and causing excessive wear on the drivetrain components. ANSYS Maxwell was used for finite element analysis, and the designs were optimized using a genetic algorithm to vary the stator slot height and width for both machines and rotor slot dimensions for the WRSG. This was done by giving the algorithm maximum, minimum, and starting values for the widths and heights. The starting values were the values calculated for the conceptual design. The performance of the generators were compared by examining their torque ripple reduction and any resultant effects on either generator to determine the ideal machine for wind turbines. The WRSG is a non-permanent magnet generator that features a fixed stator and a three-phase winding and a rotor connected to slip rings, operating through magnetic field interactions. Its design allows for reactive power control via flux variation and direct grid connection without needing a solid-state converter. The WRSG can have different winding configurations for the stator, which are the overlapping and non-overlapping configurations. There are also three main slot types used in electrical machines, and these are the open, semi-closed, and tapered slots. This study made use of rectangular open slots for ease of design and potential manufacturing, as the coils are preformed and then slotted in. The PMSG is a brushless design using permanent magnets for superior power to volume and torque to inertia ratios compared to other electrical machines. The rotor options for its design are surface or interior permanent magnets. For this study, we opted for surface permanent magnets. These were chosen for efficiency, as fewer magnets are required, but unfortunately, this comes with speed limitations due to weaker mechanical strength than the interior permanent magnets. PMSGs and WRSGs each have their own advantages and disadvantages. The size and weight of PMSGs make them suitable for weight-sensitive applications, but they are often made from rare earth metals that are expensive. They can be used for both fixed speed and variable speed systems. However, they require careful synchronization during startup and precise voltage regulation due to their sensitivity to operating conditions. WRSGs are generally larger and increase in size and weight with higher pole numbers, limiting their use in weight-sensitive applications. They can independently produce reactive power for enhanced voltage regulation, but are limited by the need for brushes. This leads to increased maintenance requirements and potential reliability issues. Torque ripple is the uneven torque production through the rotation of an electrical machine, caused by variances in the electromagnetic fields and their interactions between the stator and rotor. Torque ripple is mathematically defined as the difference between the maximum torque and minimum torque produced over one mechanical revolution, divided by the average torque, which is converted to a percentage. The primary cause of torque ripple is the armature reaction. As the current increases, the flux shifts, which creates harmonics in the torque constant waveform. It can be reduced in a number of ways, such as skewing of the rotor magnets or stator slots, permanent magnet shifting, different slot width pairing, or reducing the flux harmonics. This study looked at adjusting the slot widths for torque ripple reduction. Genetic algorithms are a prevalent optimization method for electrical machines. It is a process that involves seeking the minimum or maximum of a function in multidimensional spaces, and was the process used in the study. This begins with an initial population that evolves iteratively through selection, where each solution is evaluated using a fitness function. Reproduction is based on fitness, favoring fitter candidates, and introduces new traits through crossovers and mutations. While not guaranteeing the best solution, this approach yields multiple good solutions. This process continues until a specific criteria is met. For the WRSG, the tangential stress was calculated based on the machine specifications. The rotor size was determined, allowing for calculations of the machine length. The air gap was calculated, determining the stator size. The turns were calculated using a winding factor according to the machine specifications. To determine the dimensions for the slots of the rotor and stator, the stator and stator current had to be determined. The areas of the conductors were primarily determined by the current densities in the stator and rotor windings, as well as the number of parallel paths. The area of the slots were determined with the areas of the conductors and by taking the space factor into consideration. The PMSG had a similar design process. It started with determining the machine coefficient according to the machine specifications and winding factor. The inner stator diameter was determined according to the specified power output. The length of the machine could also then be calculated. The air gap was calculated, determining the stator size. To determine the dimensions for the slots of the stator, the phase current had to be determined. The areas of the conductors were primarily determined by the current densities in the stator windings. The depth of the stator core and the width and the height of the stator slot could then be calculated, which allowed for the outer stator diameter to be calculated. The size of the magnets of the PMSG were based on properties such as flux density and magnetizing force of the neodymium iron boron 48H permanent magnet, which was the chosen magnet. The conceptual design results confirm that the design met the desired specifications of being a 3 megawatt electrical machine with a 16-18 pole slot configuration. The results showed that the WRSG stator outer diameter of 1.65 meters and a rotor outer diameter of 0.984 meters. However, the smaller PMSG had a stator outer diameter of 1.26 meters and a rotor outer diameter of 1.039 meters. The PMSG made use of permanent magnet designed with a height of 8.31 millimeters and a width of 122.86 millimeters. ANSYS Maxwell was used to create a 2D model of the WRSG and PMSG. It was then used to calculate torque, induced voltage, eddy currents, and core losses. This was done by implementing the conceptual design into ANSYS Maxwell, which could then be simulated and analyzed. It provided the starting point for the optimization, as well as allowing for the optimized model to be simulated and analyzed. The optimization only focused on reducing the torque ripple in relation to the given slot parameters and did not look at reducing the losses in the electrical machine, which can be seen by the large stator yoke. The WRSG was optimized in ANSYS Maxwell by using a genetic algorithm, which was terminated after 425 iterations. The maximum heights were 280 millimeters for the stator and 200 millimeters for the rotor. The maximum widths were 170 for the stator and 100 millimeters for the rotor. The minimum heights were 95 millimeters for the stator and 85 millimeters for the rotor. And the minimum widths were 32 millimeters and 27 millimeters for the stator and rotor. These sizing constraints for the slot dimensions are shown in the table, as well as the optimized values of 129.85 millimeters and 42.15 millimeters for the stator's height and width, and 136.2 millimeters and 49.44 millimeters for the rotor height and width. These optimized values were close to the original conceptual design values. The results were recorded from the designed and optimized models. The graphs on the left show the torque, average torque, and torque ripple. We can see that the torque ripple is lower in the optimized model, the bottom graph on the left. The graphs on the right show the rotor core loss, stator core loss, rotor eddy current loss, stator eddy current loss, rotor hysteresis loss, stator hysteresis loss, and stranded loss. The design torque ripple was higher than the targeted 6%. However, after optimizing the design, the torque ripple was reduced to 5.577%. But the output power of the design also decreased by 9.38%, as the average torque went from 88.5 kilonewton meters to 80.20 kilonewton meters. The PMSG was also optimized with the genetic algorithm, which was terminated after 425 iterations. The maximum and minimum constraints for the slot dimensions are shown in the table, as well as the optimized values of 54.16 millimeters and 79.78 millimeters for the stator height and width. The results were recorded from the designed and optimized models. The graphs on the left show the torque, average torque, and torque ripple, where we can see the torque ripple is low in the optimized model as well, which is also the bottom left graph. The graphs on the right show the rotor core loss, stator core loss, rotor eddy current loss, stator eddy current loss, rotor hysteresis loss, stator hysteresis loss, and stranded loss of the designed PMSG model. The designed PMSG model had a higher than designed torque ripple, just like the WRSG, which was also reduced to below 6% after optimization, to a value of 5.89%. However, the output power of the design also decreased by 11.24%, as the average torque went from 74.5 kilonewton meters to 66.12 kilonewton meters. However, even though both the WRSG and PMSG showed desirable torque ripple reductions, the WRSG had a 34.94% reduction in torque ripple, with a 9.38% loss in output power, while the PMSG achieved a 37.23% reduction in torque ripple, with 11.24% decrease in torque output. This shows the efficiency of the optimization process in reducing torque ripple, with the WRSG demonstrating more efficient trade-off between torque loss and torque ripple reduction compared to the PMSG. The optimization process impacted the PMSG's torque more significantly, leading to reduced power output. The WRSG outperformed the PMSG with a higher efficiency. The optimization process did not impact the WRSG's torque as much as the PMSG's torque, because it effectively reduced cogging torque and harmonic content. However, the optimization process reduced the effective area of the slot when changing the slot size parameters for both generators. This reduced the output torque more significantly in the PMSG, which led to reduced power output. The WRSG experienced higher stator core losses since the machines operated at the same frequency. Another factor that contributed to core losses was flux density. Thin magnets were used, which led to reduced flux density in the core. Thus, the machine was not saturated, leading to fewer losses. The low flux density was evident given the fact that the torque was low compared to the WRSG. The WRSG exhibited significantly lower stranded losses compared to the PMSG. Lower stranded losses can result from either lower current or lower resistance. The WRSG had a larger conductor area, thus lower resistance. resulting in lower stranded losses. The stranded losses remained constant for both the conceptual design model and the optimized model, as the optimization process did not alter any specifications which would have changed the stranded losses of both the PMSG and WRSG. The objective was to design and optimize a WRSG and a PMSG to achieve a torque ripple of below 6%. The optimization process involved adjusting stator slot widths and heights for both the WRSG and PMSG, as well as the rotor slot dimensions for the WRSG to minimize the torque ripple. The conceptual design process resulted in the specification being determined for a 3 megawatt 16-18 pole slot operating at 375 RPM for a WRSG and PMSG. The specification results showed that the PMSG had a better power to volume ratio, evident in the smaller design volume of the PMSG with 1.3 meters cubed compared to the WRSG's volume of 3.21 meters cubed. Implementation of the conceptual design into ANSYS Maxwell allowed for finite element analysis, FEA, confirming the design process to the output torque being within acceptable ranges as per the design specifications. The FEA also allowed for the efficiency to be calculated by taking into account the losses in the system. The conceptual designs were then optimized using a genetic algorithm. The optimization process focused on determining optimal stator slot dimensions for both the generators. To minimize torque ripple within 425 iterations each, this was successfully achieved, and it reduced the torque ripple. However, both the WRSG and PMSG had a reduction in torque output. For the study, it is clear that the WRSG outperformed the PMSG in terms of torque ripple reduction, with the RSG achieving a low value of 5.577% compared to 8.90% for the PMSG. With minimal torque loss during the optimization process. Despite the WRSG's larger volume compared to the PMSG, its torque ripple, torque output, and efficiency show that it is the preferred choice to be used in wind turbines.
Thank you very much, Tariq. Ladies and gentlemen, please, if you have any questions, please type it into the questions panel. At the moment, we don't have any questions, but if you have any questions for Tariq, please ask them now, and we'll get him to answer. I'll give you a few moments. While you type your questions, please, if you would like to join the SAIEE Rotating Machine Section, please send an email to rmsection@saiee.org.za. You will also see in the handout section on the webinar the PDF document of the latest issue of the What Now magazine, the May issue, and as well as the SAIEE Training Academy brochure for CPD courses that we have. Any questions, please ask them now. Type them in the questions panel. I'll give it a few more moments. Yes, I've got a question here. Thank you very much. Emmanuel Augusto asking Tariq, are protection philosophies the same for both WRSGs and PMSGs?
Hold on, can you see me? Hello? Yes. Sorry, can you repeat the...
The question is from Manuel Augusto asking, are protection philosophies the same for both WRSG and PMSG?
Not that I'm aware of, but the sort of the focus of this was more to look at the torque ripple reduction in the two machines, rather than the actual implementation and the use of them in wind turbines. So it was more focused on seeing if I could reduce the torque ripple and then use them in wind turbines, and not really on a lot of other stuff. That answers the question very vaguely.
No problem. Thank you. I've got a question here which is not related to you, from Quentin van der Merwe. Will there be a download link? Yes, Quentin. If you register on the SAIEE TV channel, the link is in the chat box. The recording of this webinar will be uploaded later this afternoon, and then you're welcome to watch it live or download it. Any other questions for Tariq, ladies and gentlemen? Any questions from the audience there in the room?
What would you like to further
So if I were to take this further, I think I would have liked to actually build the machine, which would be great to do. And then also looking a little bit more at the financial implications of actually getting this done. As I mentioned briefly at the beginning, I spoke a bit about like the transportation and the building, as well as the fact that I chose to use rare earth metals as my permanent magnets for my PMSG design. So I think taking all these things into consideration, as well as maybe looking more into the reduction of the losses in the machines, instead of just looking at the torque ripple reduction, would give a little bit more clarity on the final decision of which to actually use. Yes.
I've got a question here from the online audience from Reino Gerber. He says, good day, this was an interesting study. I assume this WRSG will be directly connected to the grid. What is the active and reactive power compensation of these machines under fault conditions, and how does this compare to a PMSG? That's the first question. Do you want to answer that first and I'll go to the second one?
I can, but so I didn't actually look at connecting it to the grid. So I didn't look at the reactive power. I was just looking at seeing if I could get the torque ripple lower on these electrical machines to use. So I can't exactly answer that question.
Okay. The second part of his question says, did you account for the field copper losses in your WRSG?
Yes, I include my core losses and my winding losses.
Okay. Any other questions, ladies and gentlemen?
There's one here as well. Hold on. Yes.
Absolutely.
Did you ever try to see if you keep torque at 88? You see how you can optimize things like asking the torque down, whilst maintaining the high torque.
So anytime I started affecting the effective area of these like slot shapes, no matter what I did, the torque would just always come down.
So Tariq, I've got no questions from the online audience now. So I think from my online side, ladies and gentlemen, I want to thank you for your attendance. Tariq, thank you very much for your availability to present. Yes. Sorry.
Okay. There's one more question here. Sorry, on the side in the room.
Okay, we'll take one more question.
Application of your system in wind turbines. There are problems mainly with this data, power cutting in this data. Those are the open circuit, short circuit, those are the normal problems. Within this area, ripple protection, according to this system, can help to solve the problem, minimize the problem.
So not necessarily in the PMSG. I think a better solution for the PMSG is the shifting of the permanent magnets, not this process of changing the slot dimensions. I think that would be the way to go for using PMSGs in wind turbines.
Okay, so that will bring us to the end to the webinar. Tariq, thank you very much for giving us this presentation. Ladies and gentlemen, online audience, thank you very much for your time. For the physical attendance audience from the Rotating Machine Section, thank you very much for allowing us to have this prize-winning presentation, sharing it with all our members globally. And please watch out for the recording on the SAIEE TV channel. I thank you for your availability and for your presence. Have a good day. Goodbye.
Thank you.